Hello, everyone, and welcome to another episode of the GC 100 podcast. I'm your instructor and host, Dr. VG. All right, today we're going to be covering one of my favorite topics, lake effect snow. And so we're going to really kind of be like applying some of the atmospheric and weather air circulation understanding from the previous lecture topic here to better understand how and where lake effect snow develops. So let's begin here with a picture of, in this case, it's actually in Buffalo, New York, also a very distinct area receiving lake effect snowfall near Lake Ontario. And so here, shoveling the roof, a common activity here in Michigan as well, due to the excessive abundance of lake effect snow that we receive. All right, enough about that. Let's get going. So, how does this work? So, or before I begin, too, I want to just kind of point out that this lecture is very much dedicated to exercise 8, which is focused on interpreting and applying our understanding of the content that I'm about to deliver, which is also tied to some of the previous lecture content. So I'll jump back in. It has everything to do at the very beginning with the location of the polar jet stream. And in fact, some of the world's most sophisticated computer models, literally like huge data centers, powering the forecasting of this polar jet stream. And so, in order to forecast or predict the position and the movement of this polar jet stream over time, it requires an incredible amount of computational power. And so we can observe this using satellites in real time, but to forecast it into the future is incredibly computationally comprehensive. And it's also why our forecasts are only so good. And really, especially here in North America, it all begins with this relative position of the polar jet stream. So what is it? It's this concentrated jet of air where wind speeds are incredibly high, and it really truly demarks or literally is a boundary between Arctic air and mid-latitude air. And these are very different air masses, and they effectively don't mix. It's like this boundary that is distinctly separating what is known as the polar vortex, this cold air up to the north, from this kind of warm, more temperate mid-latitude air. And so this image kind of depicts this large undulation known as a Rossby wave within the polar jet stream. But I want to appreciate that this polar jet stream completely circumnavigates the northern hemisphere. And so I have an image and a video on the next slide to kind of appreciate that. But I do, before we jump to that, I want to just emphasize here's the UP in Marquette, Michigan, where the cursor is. And in this image, we are effectively north of the polar jet stream. And so the jet stream being here to our west and south, but again, we're like to the north, meaning we're inside of that polar vortex, this polar cell of air, which is cold, dry air. And whenever that happens, what occurs is you have this cold, dry air from the Arctic and from northern Canada coming down, and it gets pulled across Lake Superior, like this blue arrow is showing. And so that is the recipe, so to speak, to set up lake effect snow. And so now we'll better understand the factors leading up to that. And so again, this polar jet stream to our south being key, and it's pulling this relatively cold air, or definitely cold air, across Lake Superior. So I like this animation, and it literally is this multi week or day period of polar jet stream circulation here, and where there's red, there's high wind speeds, and so here is the North Pole, and then we're going around. Here's Alaska just as a reference, but this jet stream literally circumnavigates the northern hemisphere, and within this region, then we have our Arctic or polar air masses, and then we have the kind of more mid-latitude temperate air masses to the south all the way around this. So let's watch this animation as this movement in the pattern is highly chaotic, I guess, in a way, for lack of a better word. So let's see. Oh no, there we go. Try it now. All right, so as you can see, there is this kind of movement or undulation, especially as we start focusing on North America, where wind speeds get higher and then lower. The relative position is kind of like an undulating. It's almost like you whip a rope. I'm going to pause it too here to kind of just show these really large undulations or dips, and you can really here see kind of Lake Ontario and the eastern Great Lakes. At least in this image, Lake Superior would be somewhere in here, but appreciate that this is just kind of always changing and evolving, and the relative position of this undulation can move east or west and north or south. And so I'll just kind of keep going with this to show you how this evolves over time. And then here, another kind of spot where it's now a high pressure circulating, but this definitely a polar jet stream now to the north of Lake Superior. And whenever that happens, at least in the winter, we do not expect lake effect snow, at least to be affecting Marquette, because really what that means is we have mid-latitude air masses and even further south, maritime getting pulled up, and that's what our air masses influencing Lake Superior at that time point are coming from the south and from the southwest, and they're no longer coming from the north. So just kind of jumping out, move a little further. Let's go a little further in time. And so here again, a definitive band of that jet stream here. It's kind of right over top. You can see Lake Michigan here to the south, and it goes on and it's undulating. And so it's moving, and this is what brings in cold air masses are coming down here in this image right here, down into the northern US states, moving even further, and then it kind of moves off into our east and out into the Atlantic. So let's escape out of there. Oops, I'll have to do this and then come back with my laser pointer. All right, back in action. So there's the animation as it moves through. So now to our next step. So phase one, if you will, is that polar jet stream needs to be located south of the Upper Peninsula in order to draw Arctic air from the north down across Lake Superior. And so now let's think about what happens when that cold, dry air moves across to Lake Superior. Before we get there, has anyone heard of Hakenpaiva? Well, it's a snow festival in the middle of the winter, and it occurs that this Hakenpaiva occurs up in Hancock and Houghton. Here's the lift bridge, but there are other Hakenpaiva festivals across the UP. Actually, Hakenpaiva, if you're familiar, was actually just made up by a radio broadcaster in the Keweenaw in the 1970s, although it sounds like it is this other old worldly festival. But either way, during Hakenpaiva, people jump in. Have you ever done a polar plunge anywhere? I've done a few, but they typically involve saunas. And would you go swimming in Lake Superior in the middle of the winter? I know people are kind of into Wim Hof, and that is really cool. I think it's interesting, but I wouldn't really go swimming personally, unless there's a sauna involved in the middle of the winter. But back to the more important point is even though Lake Superior is like pretty darn cold in the middle of the winter, often Lake Superior is really warm compared to the incredibly cold air. And so when this cold air moves from the north across Canada and it reaches Lake Superior, it passes over a relatively warm surface. And so the key here is that Lake Superior is actually much warmer than the air. And so here in this diagram, we're going to kind of work through this diagram iteratively here for the next few slides. And so let's kind of review, or let's think a little bit. What water cycle represents when liquid water goes into gaseous or water vapor? What is that state, that change of water? What is that water cycle called? Well, it is in fact evaporation. So here, this is evaporating. So we have a relatively warm lake. We have cold air, and from this diagram, let's imagine this is the Upper Peninsula shoreline, and then you go up inland and up in elevation into Ishpeming and Negaunee, Ishpeming, and beyond. And so we have this air from in this diagram from the north coming over Lake Superior, passing over relatively warm water, where now you're adding moisture into relatively cold air. And so now let's think about this. So does evaporation increase or decrease the relative humidity of the air above the lake? Recycling and applying some of our knowledge from the previous lecture topic. So now let's think about this. If you have an air mass and it's cold and dry and it moves over Lake Superior, it does warm up a little bit, but it's still pretty darn cold. but you've now added a bunch of moisture. And so if you add moisture into an air parcel, and maybe the temperature increases a little bit, but let's just say it's still pretty darn cold. If you have a pretty darn cold air mass that you've now added moisture into, what happens to the relative humidity? Well, it in fact increases because you've added moisture. So there's more moisture, and that means you're getting closer and closer to saturation, the absolute humidity value. And so as this cold, dry air moves over the relatively warm Lake Superior, the air does warm up a little bit, but it's still pretty darn cold. But you're adding this incredible amount of moisture into the air. And at that point, as that relative humidity value increases and increases, it reaches saturation. Clouds form, which is it reaches dew point, clouds form, and it potentially begins to snow. And so you're adding this moisture in. So let's keep exploring this and kind of applying some of our previous understanding. So can an air parcel hold an infinite amount of water? Can you just keep adding water into there? And what happens then when the air parcel cannot hold any more water? It just kind of shared it on the previous slide. So let's think about what happens. It reaches absolute humidity and it condenses. And so you reach dew point, it condenses, which literally looks like clouds, rain, and or if it's cold, then snow. And so when an air parcel cannot hold any more moisture, you've reached dew point, it condenses, literally, clouds form, and it starts precipitating. And in our case, if it's cold, that is snow. And so now going back to maybe one of the kind of keystone foundational comparisons that we've been practicing, how does temperature influence the amount of water a parcel of air can hold? Another way to put it is, can cold air hold more or less moisture than warm air? Cold air can hold less moisture than warm air. So now let's tie it to an additional process or phenomenon that we talked about previously called adiabatic cooling, which then is related to orographic processes. So how does air temperature change when air pressure decreases? To apply our knowledge then, as an air parcel rises in elevation and altitude, there's less and less pressure, and so that air parcel expands and the temperature cools down. And so as air temperature decreases with increasing elevation, we then expect that air parcel to hold more or less moisture. Less moisture because as temperatures cool down, cold air holds less and less and less moisture than warm air. So now let's kind of connect many pieces across together. So we have cold air moving from the north. It moves over this relatively warm air, warm lake, and you're adding an incredible amount of moisture through evaporation. You reach dew point, it condenses, clouds form, and it starts snowing. Now that air reaches the land surface, which is colder than the lake, the air cools down, and then it also goes up, or it can go up in elevation, which is adiabatic cooling. So now you're forcing this air parcel to go up 1,000 or thousands of feet, and it's cooling even more. And because cold air holds less moisture than warm air, it literally snows more because it's like getting rid of it, can't hold anymore, and it holds even less and less. And so often you might expect kind of like light snow near the shoreline of Lake Superior, like in Marquette. And then if you go inland up to Negaunee and Ishpeming and Michigami, often there is much more snow, literally. And if you look at annual averages of snow accumulation in Ishpeming versus Marquette, literally in any given year, Ishpeming receives like 60, 80 inches, even 100 inches more snow than Marquette. And it's simply because it is almost 1,000 feet higher, and that means the air cooled down that much more, and there was that much more snow falling at high elevations. So to connect a lot of these things that we're talking about and maybe to have someone else present them to you, there's this really nice article by Michigan Live, and then here's the link to the article and then the direct hyperlink to that video reviewing some of this same content that we've been covering. So as an animation, cold air moves from the north because the jet stream is to our south. It moves over this relatively warm lake water, which adds moisture into cold air, at which point you reach dew point, it condenses and clouds form, and it may even start snowing. That cold air that's now at absolute humidity, it's snowing, moves up in elevation and gets even colder, which means it holds even less moisture, and that means it snows even more as that air rises due to orographic uplift, which is then physically known as adiabatic cooling. And you have voila, lake effect snow. Amazing. So some cool images here collected by a satellite showing this lake effect snow from space. And so this is actually Lake Superior, and you really can't see this northern shore of Lake of the Upper Peninsula. You can faintly see the Keweenaw, and then Marquette would be in here, moving over all the way into kind of Sault Ste. Marie. And so here you have this cold air coming from the north, moving over relatively warm lake water where there's evaporation, clouds form, and it may even start snowing. And then if you look kind of closely, it's even denser white here and then here. And so it moves inland over Michigan and often up in elevation, and you have even more snow. And the same phenomenon occurs downstate where that cold air moves over Lake Michigan onto the lower peninsula of Michigan, if you will, and then it starts, or there's lake effect snow for the same reason. So just a few kind of graphics to connect all the pieces. Again, one major part in the beginning is this polar jet stream is to our south. And so this image, that polar jet stream is located down here somewhere, and it's pulling this cold air from the north over relatively warm lake water, and it reaches dew point, at which point it condenses, clouds form, and it may even start snowing, and then it snows even more with adiabatic cooling due to this increase in elevation. And so here's a shaded relief map just to kind of give you a reference. Lake Superior, and then there's this big, so Marquette's down in this pocket, and then here is kind of like Ishpeming and Michigami, and this region receiving almost 100 inches more snow on any given year than Marquette. And then here's similarly this ridge or spine of the Keweenaw having a pretty dramatic elevation gradient. You have this cold air and lots of lake effect snow in this region. And so with that, I encourage you to use what you learned here to apply your knowledge in exercise 8. Dr. VG is signing off.